July 1st, 2025. A routine night at the ATLAS telescope facility in Chile. The robotic scanner swept across the southern sky, hunting for asteroids that might threaten Earth. At 14:37 Universal Time, a computer algorithm flagged something unusual, a moving dot among the stars. Within hours, astronomers realized they weren't looking at another space rock from our solar system. The numbers told an impossible story. This object was moving at 130,000 miles per hour. That's fast enough to cross the entire United States in under 3 minutes. But speed wasn't the strangest part. The trajectory was all wrong. Instead of the elliptical orbit that binds objects to our sun, this visitor traced a hyperbolic path through space. The mathematics were unmistakable. This thing came from another star system entirely. They called it 3I/ATLAS. The I stands for interstellar. The third confirmed visitor from the space between stars. The discovery triggered an immediate response across the global astronomy community. Telescopes in Hawaii, California, and Chile swiveled toward this cosmic intruder. The Hubble Space Telescope interrupted its scheduled observations. The James Webb Space Telescope prepared for emergency target acquisition. Everyone wanted to study humanity's latest visitor from the deep. But there was a problem. A cruel quirk of orbital mechanics meant this object would spend only months in our neighborhood before disappearing forever into the galactic night. The clock was ticking. This wanderer had traveled for millions of years to reach us, carrying secrets from an alien star system. Now we had perhaps 6 months to unlock those mysteries before it vanished beyond the reach of our most powerful instruments. As the first detailed observations arrived, astronomers faced a troubling realization. This wasn't behaving like the previous interstellar visitors. Oumuamua had shown mysterious acceleration. Borisov had acted like a normal comet. But 3I/ATLAS was different. It was producing gas and dust like a comet, but the chemistry was all wrong. The ratios didn't match anything in our solar system. The brightness patterns defied explanation. The very presence of activity at such distances challenged our understanding of how icy bodies should behave. Some researchers began asking uncomfortable questions. What if this wasn't just another chunk of interstellar debris? What if we were looking at something deliberately engineered? The possibility seemed absurd, but the universe has a way of challenging our assumptions about what's possible in the cosmic dark. As 3I/ATLAS raced toward its closest approach to the Sun, scientists prepared to test hypotheses that range from exotic natural physics to genuinely artificial origins. The story that would unfold over the coming months would push the boundaries of astronomy, challenge our understanding of interstellar space, and force humanity to confront fundamental questions about our place in a universe that might be far stranger than we ever imagined. Sometimes the most profound mysteries arrive disguised as routine observations. A single dot moving against the stellar background. A computer algorithm's flag in the data stream. The beginning of questions that would reshape how we think about the space between stars. Understanding what makes 3I/ATLAS special requires diving into the mathematics of motion. Every object in our solar system follows predictable rules. Planets trace ellipses around the Sun. Asteroids and comets, no matter how eccentric their paths, remain gravitationally bound to our star. These bound orbits have eccentricity values less than 1. Think of eccentricity as a measure of how stretched an ellipse becomes. Earth's nearly circular orbit has an eccentricity of 0.02. Halley's Comet, with its elongated 76-year journey, reaches 0.97. But no object born in our solar system exceeds the magic number. 1. 3. I/ATLAS shattered this boundary with an eccentricity of 1.47. That number represents freedom. This object will never return to our neighborhood. It's following what mathematicians call a hyperbolic trajectory, a path that opens into infinity rather than closing into a loop. The velocity measurements confirmed the mathematics. At infinite distance from our Sun, 3I/ATLAS would still be moving at 25 kilometers per second relative to the solar system. That's the kinetic signature of another world entirely. Momentum inherited from a star system where different physics governed planetary formation. To appreciate this speed, consider that Earth orbits our Sun at about 30 kilometers per second. 3. I/ATLAS is moving nearly as fast relative to our entire solar system as our planet moves around its star. That's not the gentle drift of local debris. That's the ballistic trajectory of something launched from cosmic distances. The rarity of such discoveries underscores their significance. The ATLAS survey system scans millions of square degrees of sky, cataloging hundreds of thousands of objects. In nearly a decade of operation, it has found exactly one confirmed interstellar visitor. These cosmic nomads are perhaps 1,000,000 times rarer than typical near-Earth asteroids. Yet theoretical models suggest the galaxy should be full of wandering debris. Every planetary system likely ejects material during its chaotic formation phase. Gravitational encounters with giant planets can fling smaller bodies onto escape trajectories. Close stellar flybys can strip outer disk material entirely. The detection challenge isn't scarcity, it's geometry and timing. Interstellar objects spend most of their existence in the cold emptiness between stars, invisible to our telescopes. Only during brief passages through stellar neighborhoods do they warm enough to become detectable. We're essentially trying to catch bullets in flight. Objects moving at interstellar velocities traverse our detection zones in months, not years. By the time we spot them, they're often already racing toward the exit. The technological revolution in wide-field surveys has finally given us the tools to find these cosmic needles in the galactic haystack. Automated systems process thousands of images per night, comparing new observations against stellar catalogs, flagging the handful of moving objects that deserve human attention. 3. I/ATLAS represents the cutting edge of this new astronomy. A field that barely existed a decade ago now routinely discovers visitors from other star systems. Each detection adds to our understanding of the vast debris field that fills interstellar space. The confirmation process follows rigorous protocols. Multiple observatories contribute positional measurements. Orbital mechanics software calculates trajectories. Independent analyses test whether the motion requires interstellar explanation or could result from solar system origins. Only when all alternatives are exhausted does an object earn its interstellar designation. The I in 3, I/ATLAS, isn't just a label. It's a certificate of cosmic citizenship, confirming this visitor's credentials as an authentic messenger from the space between stars. The story of interstellar visitors is surprisingly recent. Until 2017, these cosmic wanderers existed only in theoretical papers. Astronomers knew they should exist, but finding them proved nearly impossible with the technology of previous decades. Then came one, Oumuamua, discovered by the Pan-STARRS telescope in Hawaii. This elongated object, tumbling through space like a cosmic cigar, became humanity's first confirmed interstellar visitor. Its name, Hawaiian for scout or messenger, seemed prophetic. Oumuamua behaved strangely from the start. It showed no signs of cometary activity, no coma or tail, despite passing close to the Sun. Its extreme elongation, at least 5 times longer than wide, was unlike any asteroid in our solar system. Most puzzling, it began accelerating away from the Sun without explanation. The acceleration was tiny but measurable, roughly 1/10,000th of Earth's gravity. Multiple observatories confirmed the effect. Natural explanations struggled to account for this mysterious force acting on what appeared to be an inert rock. 2 years later, 2I/Borisov arrived as Oumuamua's civilized cousin. Here finally was an interstellar visitor that behaved like astronomers expected. It developed a bright coma and prominent tail, outgassing water vapor and carbon monoxide like a proper comet. But Borisov carried its own chemical surprise. The carbon monoxide abundance far exceeded anything seen in solar system comets. Its chemistry suggested formation in an environment colder than our outer planetary region, perhaps around a star with a more extended disk of icy material. The pattern seemed established. Interstellar visitors would be rare, exotic, and chemically distinct from solar system objects. Each would carry chemical fingerprints encoding the conditions around distant stars. Then 3I/ATLAS arrived, and the pattern collapsed. This third messenger combined features from both predecessors while adding entirely new mysteries. Like Borisov, it showed clear cometary activity with gas and dust production. But like Oumuamua, its behavior defied conventional physics in subtle ways. The chemistry was revolutionary. Where Borisov had shown carbon monoxide enhancement, 3I/ATLAS dominated with carbon dioxide. The progression suggested a sampling of formation environments so diverse that each visitor might represent fundamentally different stellar conditions. The size estimates added another puzzle piece. Oumuamua stretched roughly 400 meters in length, but only 40 meters in width, a cosmic needle. Borisov's nucleus measured about half a kilometer across, typical for a mid-sized comet. 3I/ATLAS fell somewhere between, potentially much larger but shrouded in its own luminous atmosphere. The discovery circumstances differed dramatically too. Oumuamua was found racing away from the sun, spotted almost by accident during routine surveys. Borisov arrived with months of advance warning, allowing detailed preparation. 3I/ATLAS hit the sweet spot, discovered far enough out for planning, but close enough for immediate study. Statistical analysis revealed the significance of finding 3 visitors in less than a decade. If interstellar objects follow random arrival patterns, the probability of 3 detections in such a short period suggests either remarkable luck or a much larger population than theoretical models predicted. The implications rippled through planetary science. These weren't just curiosities from the cosmic deep. They were samples from stellar environments we could never visit directly. Each visitor carried chemical and physical evidence about planetary formation processes operating around different types of stars. The progression from mystery object to classical comet to chemical enigma hinted at vast diversity in the interstellar medium. The space between stars appeared populated by debris representing every possible formation environment, every stellar mass, every epoch of galactic evolution. As 3I/ATLAS raced toward its appointment with our Sun, astronomers realized they weren't just studying another interstellar visitor. They were witnessing the emergence of an entirely new field of astronomy, one that would transform our understanding of how planets form throughout the galaxy. The universe operates on schedules that ignore human convenience. 3I/ATLAS had been traveling for millions of years to reach our solar system, but once discovered, astronomers had mere months to unlock its secrets before it vanished forever into interstellar space. The observational timeline was dictated by cruel orbital mechanics. 3I/ATLAS would reach perihelion, its closest approach to the Sun, on October 29, 2025. But cosmic geometry conspired against optimal viewing. As the visitor approached this critical phase, Earth would be positioned on the opposite side of our star. For nearly 2 months, from late September through early November, 3I/ATLAS would be lost in solar glare. Every telescope on or around Earth would be blind to the most important phase of this interstellar encounter, the moment when solar heating peaked and the object's true nature should reveal itself, would remain hidden behind our star's overwhelming light. This left astronomers with a desperate schedule. They had roughly 3 months before solar conjunction erased their target from the sky. Then perhaps 6 weeks after reappearance in December, before the object became too faint and distant for meaningful observations. The pressure transformed routine astronomical procedures into emergency operations. Telescope time that typically required years of competitive proposals was allocated on weekly schedules. Major observatories interrupted carefully planned research programs to accommodate this cosmic opportunity. Hubble Space Telescope received priority target of opportunity scheduling. The James Webb Space Telescope dedicated precious observing time normally reserved for the most distant galaxies. Ground-based facilities from Chile to Hawaii coordinated observations with military precision. The international response resembled a carefully orchestrated symphony. As Earth's rotation carried observatories into darkness, others on different continents picked up the monitoring. Radio telescopes listened for any electromagnetic emissions. Planetary radar systems attempted to bounce signals off the nucleus. Every observation mattered because none could be repeated. Unlike periodic comets that return for multiple encounters, interstellar visitors offered only one chance to gather data. The information collected during 3 I/ATLAS's brief passage would represent the only scientific knowledge humanity would ever possess about this particular messenger from the deep. The technical challenges were formidable. The object's rapid motion across the sky pushed telescope tracking systems to their limits. As distance increased, signal-to-noise ratios degraded exponentially, making spectroscopic analysis increasingly difficult. Amateur astronomers worldwide joined the effort, contributing photometric observations that filled gaps in professional coverage. Citizen science platforms mobilized thousands of volunteers to process images and analyze light curves. The entire global community participated in humanity's most intensive study of an interstellar visitor. Data analysis proceeded at unprecedented pace. Normally, astronomical observations might take months or years to process and publish. For 3 I/ATLAS, researchers compressed analysis into days or weeks, sharing preliminary results through telegrams and preprint servers almost as soon as observations were complete. The approaching solar conjunction added dramatic urgency to every measurement. Scientists knew they were witnessing phenomena that would never repeat. This specific configuration of orbital mechanics, stellar heating, and terrestrial viewing geometry was unique in cosmic history. Mars' orbital assets offered a tantalizing possibility for observations during Earth's blackout period. The Mars Reconnaissance Orbiter would have a clear view of 3 I/ATLAS during its October approach, potentially providing crucial data when Earth-based telescopes were blind. As summer progressed toward autumn, the astronomical community found itself in a race against celestial mechanics. The clock was counting down to solar conjunction with relentless precision. Every clear night, every successful observation, every spectrum captured brought them closer to understanding this enigmatic visitor. The irony wasn't lost on researchers. They were studying something that had survived million-year journeys through the cosmic void, yet their opportunity to examine it was measured in months and constrained by the simple fact that Earth orbits the same star. When Hubble Space Telescope first focused its mirror on 3 I/ATLAS on July 21, 2025, the image that emerged challenged every expectation astronomers had built about interstellar debris. The visitor appeared as a soft, teardrop-shaped glow against the star-studded darkness, beautiful and utterly perplexing. The nucleus itself remained frustratingly unresolved, appearing as nothing more than a bright point source buried within its own atmospheric shroud. But Hubble's exquisite optics allowed scientists to constrain its size. No more than 5.6 kilometers across, roughly the size of a small city, yet somehow generating a coma that stretched thousands of kilometers in every direction. This scale mismatch became the first major puzzle. How could such a tiny nucleus produce such an enormous atmosphere? Solar system comets followed predictable relationships between nucleus size and coma extent. 3 I/ATLAS seemed to violate these established patterns. The imaging revealed structure within the coma that hinted at complex physics. The dust distribution wasn't perfectly smooth. Subtle variations in brightness suggested active regions on the hidden nucleus surface. Specific locations venting material into space in patterns that Hubble could detect, but not resolve. Most intriguingly, The coma showed a distinct elongation pointing toward the sun. This seemed counterintuitive. Conventional physics demanded that material should flow away from solar heating, not toward it. The apparent sunward drift puzzled observers until they realized viewing geometry could create optical illusions in three-dimensional gas flows. The expected anti-solar tail, that classic feature blown away from comets by solar radiation pressure, remained stubbornly invisible. Theory insisted it should exist. Computer models predicted its formation. But Hubble's sensitive cameras found only the faintest hints of material streaming away from the sun. This absence became a source of heated debate. Was the tail genuinely missing, suggesting unusual dust properties or exotic physics? Or was it present but compressed by viewing angle into near invisibility? The uncertainty would persist until late August, when ground-based telescopes finally confirmed the tail's existence. Photometric analysis revealed another anomaly. 3. I/ATLAS appeared brighter than expected for an object of its estimated size. This suggested either a larger nucleus than Hubble could resolve, or surface materials with unusually high reflectivity. Both possibilities raise questions about composition and origin. The brightness remained remarkably stable across weeks of observation. Most comets show periodic variations as rotating nuclei present different faces to observers. The absence of such changes in 3 I/ATLAS implied either very slow rotation, nearly pole-on viewing geometry, or uniform surface properties that masked rotational effects. Hubble's tracking observations created accidentally artistic images. Keeping the comet centered in the field of view, the telescope recorded background stars as bright streaks across the frame. The result transformed scientific documentation into ethereal art, showing 3 I/ATLAS flying through tunnels of light. The dust loss rates measured by Hubble provided crucial constraints on the visitor's activity level. The object was shedding material at rates comparable to solar system comets observed at similar distances from the sun. This might have seemed reassuring, evidence of normal behavior, except for one crucial detail. This nucleus had been wandering interstellar space for millions of years, exposed to cosmic radiation that should have fundamentally altered its surface chemistry. Yet here it was, behaving like a fresh comet on its first passage through the inner solar system. The contradiction deepened the mystery. How could something so ancient act so young? The surface should have been processed by high-energy particles, depleted of volatile materials, covered with radiation-resistant crusts. Instead, 3 I/ATLAS appeared chemically naive. As Hubble continued monitoring through July and August, each observation added complexity rather than clarity. The visitor was revealing itself to be unlike any interstellar object in the limited catalogue humanity had assembled. The stage was set for more sophisticated analysis. Hubble had established that 3 I/ATLAS was active, unusual, and fundamentally puzzling. But understanding its true nature would require instruments capable of analyzing the chemistry hidden within that luminous coma. August 6, 2025, marked a revolution in our understanding of 3 I/ATLAS. The James Webb Space Telescope, humanity's most powerful infrared eye, captured the visitor's spectral signature and delivered results that shattered every model of interstellar comet chemistry. The numbers told an impossible story: carbon dioxide to water ratio 8:1. To appreciate how extraordinary this measurement was, consider that most comets in our solar system show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most water-poor comets rarely exceed carbon dioxide to water ratios of 2:1. Yet here was 3 I/ATLAS, flaunting a chemical signature so extreme it placed the object in a category of 1. The carbon dioxide abundance wasn't just unusual, it was unprecedented in the annals of cometary science. The implications rippled through theories of planetary formation. If 3 I/ATLAS had condensed from the gas phase in a protoplanetary disk, the thermodynamic conditions must have overwhelmingly favored carbon dioxide over water. This suggested formation in a zone analogous to our asteroid belt, warm enough that water existed as vapor but cold enough for carbon dioxide to freeze. But Webb's discovery was only the beginning. The SPHEREX mission's Wide-Field Infrared Surveyor revealed something even more staggering. The carbon dioxide emission extended outward for at least 348,000 kilometers, nearly 250,000 miles from the nucleus. This represented the largest carbon dioxide coma ever mapped around any comet. The scale defied comprehension. Imagine the entire Earth-Moon system, then stretch that distance another 50%. That's the size of 3 I/ATLAS's carbon dioxide envelope, a ghostly sphere of gas large enough to swallow multiple planetary orbits. The sheer extent of this emission region challenged fundamental assumptions about how small nuclei generate large comas. The physics demanded either extraordinary activity levels, far exceeding anything seen in solar system comets, or mechanisms that distributed gas sources across volumes much larger than traditional models predicted. The water detection story became equally puzzling. While Webb identified robust carbon dioxide emission lines, the water signature remained strangely muted. Some observers questioned whether 3 I/ATLAS contained significant water ice at all. This contradicted earlier Swift observatory reports that had detected hydroxyl radicals, typically indicating water photodissociation. SPHEREX added another twist by mapping absorption features at specific infrared wavelengths, consistent with water ice on or near the surface. The ice was there, locked in solid form, but something prevented it from sublimating efficiently into gas phase. Surface chemistry was hiding secrets that spectrometers could only hint at. The contrast with previous interstellar visitors was striking. 2 I/Borisov had shown elevated carbon monoxide, not carbon dioxide, relative to water. That chemical signature suggested formation in cold outer disk regions where carbon monoxide ice could condense. But carbon dioxide told a different story entirely. The temperature dependence of volatile sublimation offered potential explanations. At 3 I/ATLAS's distance from the Sun, roughly 2.5 to 3.5 astronomical units, water ice sublimation remained relatively inefficient, while carbon dioxide stayed highly volatile. Thermodynamics naturally favored carbon dioxide outgassing over water vapor production. This provided a testable prediction. If temperature effects explained the observed ratios, then post-perihelion observations should show increased water emission as the nucleus heated and cooled. The carbon dioxide to water balance should evolve predictably, based on laboratory measurements of ice sublimation at different temperatures. The extended carbon dioxide cloud raised its own questions about survival mechanisms. How does gas remain concentrated across such enormous distances? Solar-wind interactions, magnetic field effects, and radiation pressure should disperse the material much more rapidly than observations suggested. As 3 I/ATLAS continued approaching the Sun, its chemical revolution was just beginning. The August discoveries had rewritten the textbook on interstellar comet composition, but the most dramatic changes lay ahead, hidden behind the approaching solar conjunction that would soon erase the visitor from Earth's view. The accumulating anomalies surrounding 3 I/ATLAS forced astronomers to confront an uncomfortable possibility. What if they weren't studying a natural comet from another star system? What if this visitor represented something deliberately engineered? The question seemed almost absurd in the context of 21st century astronomy. For centuries, the universe had revealed itself through natural processes operating on vast scales. Stars formed according to gravitational physics. Planets coalesced from dust and gas. Comets were leftover building materials, frozen remnants of planetary system formation. But 1 Oumuamua had already challenged these comfortable assumptions. That first interstellar visitor showed mysterious acceleration, that natural outgassing couldn't fully explain. Its extreme elongation suggested either exotic natural formation or possibly artificial geometry. Radio telescopes found no signals, but silence didn't necessarily mean natural origin. Harvard astrophysicist Avi Loeb had proposed that Oumuamua might represent alien technology, perhaps a light sail or probe from another civilization. The scientific community largely rejected this interpretation, but the underlying questions remained valid. How would we recognize artificial objects in space? What signatures would distinguish technology from natural phenomena? 3I/ATLAS presented even more puzzling characteristics than its predecessor. The enormous carbon dioxide coma seemed too large for natural outgassing from such a small nucleus. The chemical ratios didn't match any known formation environment. The object appeared brighter than expected, suggesting either unusual size or exotic surface properties. Most intriguingly, the visitor's trajectory through our solar system displayed remarkable geometric properties. It would approach close enough for detailed observation while maintaining safe distances from all planets. The viewing opportunities seemed almost optimized for Earth-based astronomers. Such convenient geometry could certainly result from chance. The universe contained no shortage of cosmic coincidences, but the alternative deserved consideration. What if the trajectory had been deliberately calculated to maximize scientific observation opportunities? The timing raised additional questions. 3. I/ATLAS arrived during an era when humanity possessed telescopes sophisticated enough to study its chemistry and dynamics in unprecedented detail. A few decades earlier, most of its anomalous properties would have remained undetectable. Radio telescope observations added another dimension to the mystery. Multiple facilities monitored 3I/ATLAS across various frequencies, searching for any electromagnetic emissions that might indicate artificial origins. The silence was deafening, but advanced technology might communicate using methods beyond human detection capabilities. The theoretical framework for interstellar probes suggested such objects might be nearly indistinguishable from natural phenomena. Any civilization capable of sending missions across interstellar distances would likely design them for maximum durability and minimum detectability. Camouflage might be essential for survival in hostile environments. Self-repairing systems could maintain functionality across million-year journeys. Nuclear power sources could provide energy for decades or centuries. Sophisticated materials could mimic natural comet chemistry while housing electronic components. The technology might be virtually invisible to conventional astronomical observations. The probe hypothesis also addressed some puzzling aspects of interstellar visitor statistics. Why had humanity detected only 3 such objects in recent years after centuries of astronomical observations? Perhaps natural interstellar debris was indeed rare, while artificial visitors represented deliberate exploration missions triggered by detection of Earth's radio emissions. The timeline was suggestive. Human radio signals began reaching nearby star systems in the mid-20th century. Responses from civilizations 50 to 100 light-years away would arrive in the early 21st century, precisely when interstellar visitor detections began. Such speculations remained highly tentative, lacking the extraordinary evidence that extraordinary claims required. But the scientific method demanded consideration of all hypotheses consistent with observational data, even those that challenged conventional assumptions about cosmic phenomena. The technological interpretation of 3I/ATLAS wasn't necessarily more likely than natural explanations, but it provided testable predictions that observational campaigns could evaluate. The visitor's behavior during perihelion passage would offer crucial constraints on its fundamental nature. The possibility that 3I/ATLAS represented artificial technology rested on a foundation of observational anomalies that natural explanations struggled to address. Each unusual characteristic might have mundane causes, but their combination painted a picture that some researchers found genuinely puzzling. The brightness problem presented the most quantifiable challenge to natural interpretations. 3. I/ATLAS appeared significantly brighter than expected for an object of its estimated size. Hubble's constraints suggested a nucleus no larger than 5.6 kilometers across, yet the observed luminosity implied either much greater size or surface properties, unlike any known natural materials. Avi Loeb's calculations pushed this discrepancy to its logical conclusion. If the object possessed ordinary reflectivity characteristics, its apparent brightness would require internal energy generation of roughly 10 gigawatts. That's enough power to supply a small city, produced by an object smaller than many asteroids. The extended carbon dioxide coma presented an even more dramatic puzzle. The emission region stretched nearly 350,000 kilometers from the nucleus, larger than the distance from Earth to the Moon. For such a small nucleus to maintain gas production across this enormous volume challenged every model of natural outgassing. Natural sublimation physics imposed strict relationships between nucleus size, solar heating, and coma extent. 3 I/ATLAS seemed to violate these fundamental constraints, suggesting either unknown natural processes or artificial energy sources supplementing solar heating. The chemical composition offered additional clues. The 8:1 carbon dioxide to water ratio was unprecedented among known comets. While extreme formation environments might explain such ratios, the combination with other anomalies suggested possible artificial engineering of surface chemistry. Advanced materials, science could potentially create surfaces that selectively release specific gases while retaining others. Such technology might explain why water remained largely bound while carbon dioxide escaped so efficiently. The observed chemistry could result from deliberate design rather than accidental formation conditions. The trajectory optimization provided another piece of the technological puzzle. 3 I/ATLAS would pass through regions of space that maximized observational opportunities from Earth while avoiding gravitational perturbations from major planets. Such geometric precision could reflect intelligent navigation rather than random chance. Orbital mechanics calculations revealed the remarkable efficiency of the visitor's path. It would sample different solar heating environments while remaining visible to Earth-based telescopes for optimal duration. The trajectory seemed designed for maximum scientific impact. Radio observations yielded only silence, but this didn't necessarily support natural interpretations. Advanced civilizations might communicate using quantum entanglement, gravitational waves, or other methods beyond human detection capabilities. Alternatively, probe missions might operate in purely passive observation modes. The rotation characteristics added another anomaly to the technological case. Most small bodies in space tumble chaotically due to collision history and outgassing torques. But 3 I/ATLAS showed remarkably stable brightness, suggesting either controlled attitude or uniform surface properties that masked rotational effects. Controlled orientation would be essential for any probe system requiring precise pointing for observations or communications. The stable photometry was consistent with active attitude control using reaction wheels, gyroscopes, or other spacecraft stabilization technologies. Temperature measurements revealed thermal behavior that didn't follow simple models of solar heating. The object maintained more consistent temperatures than expected across different heliocentric distances, possibly indicating internal heat sources or sophisticated thermal management systems. The timeline correlations were particularly intriguing. If 3 I/ATLAS had originated from star systems roughly 50 light-years away, its launch would correlate with the era when Earth's radio emissions first became detectable to sensitive alien receivers. This suggested the possibility of response missions dispatched after detecting signs of technological civilization. The visitor might represent one element of a systematic exploration program triggered by humanity's electromagnetic signature. The technological hypothesis made specific testable predictions. Internal power sources should produce detectable thermal signatures. Artificial materials might show spectroscopic features inconsistent with natural formation. Controlled systems might respond to active signaling attempts. While extraordinary claims required extraordinary evidence, the accumulating anomalies deserved serious consideration through rigorous observational tests, rather than dismissal based on assumptions about what should be possible in the universe. Distinguishing artificial objects from natural phenomena in the vast emptiness of space presents one of the greatest challenges in modern astronomy. The universe produces complexity and apparent order through natural processes that can mimic the signatures we might expect from intelligence and design. Natural selection operates in cosmic environments just as ruthlessly as in biological systems. Objects that survive million-year journeys between star systems must possess specific structural and compositional properties. The interstellar medium naturally filters debris, eliminating fragile materials while preserving only the most durable combinations of elements. This cosmic winnowing process could explain many of 3I/ATLAS's unusual characteristics without invoking artificial origins. Its chemical composition might reflect natural selection pressure rather than deliberate engineering. Its structural stability could result from having survived the harsh environment of interstellar space. But genuine artificial signatures should be distinguishable from natural phenomena through careful analysis. Technological objects would likely show evidence of manufacturing processes, material properties that don't occur naturally, or behaviors that require active control systems. The search for such signatures in 3I/ATLAS focused on several key areas. Spectroscopic analysis could reveal artificial isotope ratios produced by nuclear technology, synthetic materials with properties impossible in natural environments, or chemical compositions that required industrial processing. The extended carbon dioxide coma offered one potential test. If the emission resulted from artificial systems, it might show spatial patterns or temporal variations inconsistent with natural outgassing. Controlled release mechanisms could produce geometric structures or timing patterns that passive sublimation couldn't create. Radio telescope observations maintained continuous vigilance for electromagnetic emissions that might indicate electronic systems. Natural objects in space produce only thermal radiation and occasional plasma effects. Artificial systems might leak electromagnetic signatures, even if not deliberately transmitting. The monitoring revealed only cosmic silence, no radio signals, no structured transmissions, no electronic noise that would betray the presence of active systems. This silence supported natural interpretations but didn't definitively rule out sophisticated technology designed for stealth operations. Thermal infrared analysis searched for heat sources that couldn't be explained by solar heating alone. Artificial power systems, even highly efficient ones, would produce waste heat detectable by sensitive infrared telescopes. The thermal signature of 3I/ATLAS remained consistent with passive solar heating. Photometric monitoring looked for brightness variations that might indicate artificial lighting or controlled surface properties. Natural objects typically show random or periodic variations related to rotation and surface features. Artificial objects might display controlled illumination patterns or responses to external stimuli. The optical behavior of 3I/ATLAS remained frustratingly natural. Its brightness followed patterns consistent with solar heating and dust reflection. No artificial lighting, no controlled variations, no responses to active illumination attempts by ground-based lasers. Dynamical analysis examined the object's trajectory for evidence of course corrections or attitude adjustments that would require propulsion systems. Natural objects follow paths determined solely by gravitational forces, plus minor effects from outgassing and radiation pressure. The orbital mechanics of 3I/ATLAS showed no obvious signs of artificial maneuvering. Its path through the solar system followed predictions based on gravitational physics. Any course corrections were subtle enough to remain within observational uncertainties. Perhaps most tellingly, the visitor's behavior remained consistent with known physics throughout months of observation. Natural phenomena, even exotic ones, typically follow predictable mathematical relationships. artificial systems might display behaviors that violate these natural patterns. The comprehensive search for artificial signatures yielded negative results across all categories of evidence. Radio silence, natural thermal behavior, predictable orbital mechanics, and chemical compositions that could result from exotic but natural formation processes. This didn't prove 3I/ATLAS was natural. Advanced alien technology might be indistinguishable from natural phenomena using current human detection methods, but it strongly supported conventional astronomical interpretations over technological hypotheses. The absence of artificial signatures became as scientifically valuable as their presence would have been. It established baselines for future searches and demonstrated the rigor required to distinguish genuine technological artifacts from the universe's abundant natural complexity. If 3I/ATLAS were indeed an artificial probe, its creators would have needed to solve engineering challenges that dwarf anything in human experience. Building a machine capable of surviving million-year journeys between star systems while maintaining functionality requires technologies that push the boundaries of what physics allows. The first challenge is simply staying intact across cosmic timescales. Interstellar space bombards everything with high-energy particles that gradually destroy molecular bonds. Cosmic rays can shatter electronic circuits, degrade structural materials, and alter chemical compositions at the atomic level. Any artificial probe would need materials science beyond current human capabilities. Self-repairing systems could rebuild damaged components using raw materials harvested from interstellar dust. Redundant architectures could maintain functionality even after significant degradation. Quantum error correction might preserve digital information across geological time periods. Power generation presents equally formidable obstacles. Solar panels become useless in the darkness between stars. Chemical batteries would exhaust themselves within decades. Nuclear reactors might last centuries, but would eventually consume their fuel supplies or suffer mechanical failures. The most plausible energy source would be radioisotope thermoelectric generators using long-lived radioactive elements. Plutonium-238 could provide power for decades. Even longer-lived isotopes might extend operation to centuries. But maintaining significant power output across million-year timescales would require either enormous initial fuel loads or methods of harvesting energy from the interstellar environment itself. Navigation systems would face the challenge of stellar drift. Star positions change over million-year periods as they orbit the galactic center at different velocities. A probe launched toward our solar system when both civilizations occupied different galactic positions would need sophisticated trajectory corrections to maintain its course. Autonomous guidance systems would be essential. Communication delays across interstellar distances make real-time control impossible. The probe would need artificial intelligence sophisticated enough to adapt to unexpected circumstances while maintaining its original mission parameters across timescales that exceed the entire duration of human technological civilization. The engineering requirements suggest why such probes might masquerade as natural objects. Minimizing complexity and energy consumption would be crucial for long-term survival. Systems designed to look like comets or asteroids could avoid unwanted attention while accomplishing reconnaissance objectives. Thermal management would be critical during solar system passage. A probe that had maintained near absolute zero temperatures during interstellar travel would face extreme thermal stress when approaching a star. Sophisticated materials and thermal control systems would be needed to prevent catastrophic failure. The carbon dioxide outgassing observed in 3I/ATLAS could serve multiple engineering functions. Gas release provides natural attitude control through rocket-like thrust. It creates a coma that obscures the probe's actual shape and size. The thermal effects of sublimation help regulate internal temperatures. If deliberately engineered, the 8:1 carbon dioxide to water ratio might optimize probe performance. Carbon dioxide sublimates at lower temperatures than water, providing controllable gas release across a wider range of heliocentric distances. Water retention could serve as an emergency coolant during periods of intense solar heating. The extended coma, spanning 350,000 kilometers, could result from controlled fragmentation. A probe might deploy smaller subsystems that spread throughout the solar system while maintaining communication with the primary unit. Such architecture would provide redundancy and multiple observation platforms. Data storage and transmission present their own challenges. Any probe would need to compress million years of observations into formats that could survive storage and transmission across interstellar distances. Quantum storage methods might preserve information density while resisting cosmic ray damage. The silence in radio frequencies might reflect communication methods beyond human detection capabilities. Advanced civilizations could use quantum entanglement, gravitational wave modulation, or exotic physics that leaves no electromagnetic signature detectable by Earth-based receivers. Mission parameters would require extraordinary patience from the probe's creators. They would need to launch systems knowing that results wouldn't return for millions of years, if ever. The probe's builders would be extinct long before their creation reached its destination. Such engineering challenges explain why genuine interstellar probes would be virtually indistinguishable from natural phenomena. The requirements for stealth, durability, and energy efficiency would produce systems that mimic cosmic debris almost perfectly. The possibility that 3I/ATLAS represented a reconnaissance mission rather than random debris opened fascinating questions about interstellar exploration strategies. If an advanced civilization wanted to study emerging technological societies, how would they design and deploy survey systems? The timing was particularly intriguing. Earth's radio emissions began propagating into space during the early 20th century. Television broadcasts, radar systems, and communication satellites created an expanding sphere of electromagnetic signatures that announced our technological development to any civilization monitoring nearby frequencies. By the 1950s, our most powerful transmissions could be detected across dozens of light years by receivers no more sophisticated than human technology. Military radar installations and deep space communication networks created signals that stood out clearly against the cosmic background noise. A civilization located roughly 50 light-years from Earth would have detected our earliest radio emissions around 1970. If they responded by launching probe missions using propulsion systems achieving 10 to 20% of light speed, those probes would arrive in our solar system precisely when interstellar visitor detections began. The correlation might be coincidental, but it raised provocative possibilities. What if the recent increase in interstellar object discoveries reflected not improved survey capabilities, but an actual increase in artificial visitors responding to Earth's electromagnetic signature? Strategic analysis suggested how such reconnaissance missions might be conducted. Direct high-speed intercept trajectories would be optimal for delivering probes quickly while minimizing exposure to interstellar hazards. The hyperbolic orbits of recent visitors matched exactly what probe missions would require. Multiple probe deployments would provide redundancy against individual mission failures. If 3I/ATLAS, Oumuamua, and Borisov represented elements of a coordinated survey program, their different characteristics could reflect specialized mission profiles rather than random chemical variation. Each visitor had sampled different regions of the inner solar system while maintaining safe distances from Earth. Oumuamua approached from above the plane of planetary orbits. Borisov crossed through the outer solar system. 3I/ATLAS would thread between Earth and Mars orbits during its closest approach. This geometric distribution could maximize observational coverage while minimizing the risk of detection or interference with human space activities. The visitors had studied our solar system from multiple angles without coming close enough to trigger obvious alarm responses. The chemical diversity among visitors might reflect different mission requirements rather than natural formation variations. Oumuamua's lack of visible outgassing could indicate a probe optimized for stealth operations. Borisov's normal comet behavior might camouflage a more sophisticated observer. 3I/ATLAS's unusual chemistry could serve specific technical functions. Communication protocols between probe elements would explain some puzzling observations. The object's trajectories showed loose coordination that exceeded statistical expectations for random arrivals. Their timing seemed too precise for coincidental encounters with our solar system. If the visitors were maintaining contact with each other or remote controllers, they would need communication methods beyond human detection capabilities. Quantum entanglement could provide instantaneous coordination across any distance. Gravitational wave modulation might enable communications invisible to electromagnetic surveillance. The apparent lack of direct contact attempts could reflect cautious reconnaissance protocols. Advanced civilizations might prefer passive observation over active engagement, especially when studying species that had recently developed nuclear weapons and space travel capabilities. Alternatively, the visitors might be conducting active scanning using methods we couldn't recognize or detect. Advanced sensor technologies could analyze Earth's atmosphere, biosphere, and electromagnetic environment without producing obvious signatures that human instruments would identify. The probe hypothesis made specific predictions about behavior patterns during solar system passage. Mission-oriented objects should show evidence of controlled maneuvering, systematic observation patterns, or responses to terrestrial activities that natural objects wouldn't display. Data collection phases might correlate with orbital positions that optimized viewing angles toward Earth. Navigation corrections could become apparent through precise astrometric measurements. Communication bursts might occur when probe geometries favored contact with distant controllers. The approaching perihelion passage of 3I/ATLAS would provide crucial tests of the reconnaissance hypothesis. If the visitor were artificial, its behavior during closest solar approach might reveal mission-specific activities that natural comets wouldn't perform. Solar conjunction would ironically provide the perfect cover for any probe operations that required concealment from Earth-based observations. The period when natural heating effects peaked would also offer ideal conditions for camouflaged artificial activities. The scientific method requires that even the most extraordinary hypotheses face rigorous observational tests. If 3I/ATLAS were genuinely artificial, specific signatures should distinguish it from natural phenomena, regardless of how sophisticated its camouflage might be. The electromagnetic spectrum offered the most direct avenue for detecting artificial systems. Any probe would likely contain electronic components, power systems, or communication devices that produced electromagnetic signatures distinct from natural thermal radiation. Radio telescope networks maintained continuous surveillance across multiple frequency bands. The monitoring covered traditional SETI frequencies around the hydrogen line where artificial signals might concentrate, as well as broader spectrum searches for any structured emissions that natural processes couldn't explain. The radio silence remained profound and consistent. No carrier signals, no digital transmissions, no electromagnetic noise that would betray the presence of active electronics. This absence of signals supported natural interpretations, while not definitively ruling out sophisticated stealth technology. Optical observations searched for artificial lighting or controlled reflectivity changes that might indicate active surface systems. Natural objects typically show brightness variations related to rotation, surface features, and thermal effects. Artificial objects might display controlled illumination patterns or responses to external stimuli. Ground-based laser systems attempted active communication by transmitting structured light pulses toward 3I/ATLAS. If the visitor contained optical sensors, it might respond to deliberate signaling attempts. The experiments yielded no detectable responses, though advanced systems might communicate using methods beyond human recognition. Spectroscopic analysis looked for chemical signatures impossible in natural environments. Artificial isotope ratios, produced by nuclear technology, synthetic materials with properties that don't occur naturally, or chemical compositions requiring industrial processing, would provide definitive evidence of technological origins. The carbon dioxide to water ratio, while extreme, remained within the bounds of natural formation processes. Exotic stellar environments or radiation processing during interstellar travel could potentially explain the unusual chemistry without invoking artificial explanations. Thermal infrared monitoring searched for heat sources that exceeded what solar heating alone could provide. Even highly efficient artificial systems would produce waste heat detectable by sensitive infrared telescopes. The thermal signature needed to match predictions based on known artificial power generation methods. Temperature measurements showed behavior consistent with natural solar heating and ice sublimation. No evidence of internal power sources, no thermal anomalies that required artificial explanations. The visitor's thermal evolution followed patterns expected from passive comet physics. Dynamical analysis examined orbital mechanics for evidence of course corrections, attitude adjustments, or maneuvering capabilities that would require propulsion systems. Natural objects follow trajectories determined solely by gravitational forces, plus predictable effects from outgassing and radiation pressure. The positional measurements showed no obvious signs of artificial maneuvering. 3I/ATLAS followed the smooth hyperbolic path that gravitational physics demanded. Any course corrections remained subtle enough to hide within observational uncertainties. High-resolution imaging attempted to resolve surface features or geometric shapes that might indicate artificial construction. Natural objects typically show irregular forms resulting from collision history and erosion processes. Artificial objects might display geometric regularity or surface patterns inconsistent with natural formation. Hubble's best images couldn't resolve the nucleus directly due to the surrounding coma, but they constrained overall morphology. The visitor appeared roughly spherical, with no obvious geometric features that suggested artificial construction. Particle detection experiments searched for exotic emissions that might accompany advanced propulsion or power systems. Natural comets produce predictable populations of dust particles and molecular fragments. Artificial systems might emit particles with unusual compositions, velocities, or spatial distributions. The particle environment around 3I/ATLAS matched expectations for natural outgassing. Dust grain analysis showed compositions consistent with processed interstellar materials. No exotic particles that would require artificial explanations. Perhaps most importantly, the comprehensive testing revealed no behaviors that violated known physics. Advanced alien technology might operate according to principles beyond human understanding, but it should still follow fundamental physical laws governing energy, momentum, and thermodynamics. Every measurement of 3I/ATLAS remained consistent with natural phenomena operating within established scientific frameworks. This didn't prove the object was natural, but it eliminated many scenarios that would require artificial origins. The testing protocols developed for evaluating 3I/ATLAS would provide templates for analyzing future interstellar visitors that might display more obvious artificial characteristics. As observational data accumulated throughout the summer and fall of 2025, a coherent picture of 3I/ATLAS began emerging that required no exotic physics or artificial intelligence. Natural processes, operating under conditions unlike anything in our solar system, could account for every observed characteristic of this enigmatic visitor. The carbon dioxide dominance that had puzzled astronomers since Webb's first spectroscopic measurements found elegant explanation in the physics of protoplanetary disk chemistry. Different volatile species condense at different distances from forming stars, creating distinct chemical zones as predictable as climate bands on Earth. The carbon dioxide snowline represents the boundary where CO2 transitions from gas to solid phase in the cooling environment around a young star. Objects forming just inside the water snowline but outside the carbon dioxide snowline would naturally incorporate abundant CO2 ice while remaining relatively water poor. This places 3I/ATLAS's probable birth zone in a region analogous to our asteroid belt, but around a star with different luminosity and temperature characteristics. The formation environment would be warm enough that water existed as vapor, preventing its incorporation into solid bodies, while remaining cold enough for carbon dioxide to freeze from the gas phase. The stellar environment didn't need to be exotic. Slight differences in stellar mass, luminosity, or disk properties could shift snowline positions enough to create the observed chemical ratios. The galaxy contains billions of stars with parameter ranges that would naturally produce carbon dioxide-rich formation zones. Radiation processing during the million-year interstellar journey provided additional chemical modification. High-energy cosmic rays gradually alter surface materials, breaking molecular bonds and creating new chemical combinations through radiolysis processes that operate like a cosmic laboratory. Laboratory studies of ice analog materials exposed to cosmic ray simulation showed that water molecules are preferentially destroyed, while carbon dioxide molecules show greater stability. Prolonged radiation exposure could enhance carbon dioxide concentrations while depleting water, exactly matching 3I/ATLAS's observed chemistry. The extended carbon dioxide coma found natural explanation through fragmentation models. Rather than a single solid nucleus, 3I/ATLAS might represent a loose aggregate of ice-rich fragments held together by weak gravitational and cohesive forces. As solar heating intensified, thermal stress could crack and separate these fragments, creating distributed outgassing sources across a much larger volume than traditional single-nucleus models predict. Each fragment would contribute to the overall gas production, creating the enormous coma through collective rather than individual activity. This fragmentation scenario explained several puzzling observations simultaneously. The extended emission region became understandable as the natural result of fragment dispersion. The stable brightness, despite apparent high activity, reflected the averaging effect of multiple small sources rather than brightness variations from a single tumbling nucleus. Temperature-dependent sublimation physics provided further support for natural interpretations. At 3I/ATLAS's heliocentric distance, carbon dioxide remains highly volatile, while water ice sublimation proceeds less efficiently. Thermodynamic effects naturally favor CO2, outgassing over water vapor production at these temperatures. The apparent absence of water signatures despite Spherex's detection of surface water ice suggested insulating mechanisms. Organic rich mantles could form during interstellar travel, creating surface layers that suppress water sublimation while allowing more volatile carbon dioxide to escape through cracks or thin spots. Such insulating crusts are well documented on solar system comets and would be even more likely on objects exposed to million years of cosmic ray processing. The radiation creates complex organic compounds that form refractory layers capable of selectively retarding volatile loss. Stellar dynamics explain the visitor's thick disk galactic origin. Objects ejected from planetary systems 8 to 12 billion years ago would show exactly the kinematic properties measured for 3I/ATLAS. The high velocity and unusual approach angle were natural consequences of ancient formation in the galaxy's more chaotic early environment. The orbital mechanics revealed nothing requiring artificial guidance. Gravitational encounters with stars during the interstellar journey could accelerate objects to the observed velocities while randomizing their trajectories in ways that brought them to our solar system from unexpected directions. As the pieces fell into place, 3I/ATLAS emerged as a natural wonder rather than an artificial mystery. It represented chemistry from a stellar environment very different from our own, modified by processes that operated across cosmic timescales, delivering samples of ancient galactic conditions directly to our observational instruments. Understanding 3I/ATLAS required expanding our conception of planetary formation beyond the familiar environment of our own solar system. The visitor carried chemical fingerprints from a stellar nursery that operated under conditions subtly but significantly different from those that created Earth and its neighboring worlds. Stellar mass plays a crucial role in determining the temperature structure of protoplanetary disks. Low-mass stars produce cooler, more extended regions where carbon dioxide can condense while water remains gaseous. High-mass stars create intense radiation fields that shift chemical equilibria in favor of carbon-bearing species over oxygen-hydrogen compounds. The parent star of 3I/ATLAS likely fell into the intermediate category, possibly slightly less massive than our Sun, but with different luminosity characteristics during its formation phase. Such stars are common throughout the galaxy, representing perhaps 20% of all stellar systems. The disk chemistry around such a star would favor carbon dioxide formation through several pathways. Direct condensation from the gas phase would occur at distances where temperatures dropped below CO2's freezing point, but remained above water's sublimation threshold. Chemical reactions between carbon monoxide and surface hydroxyl groups could produce additional carbon dioxide through catalytic processes on dust grain surfaces. Metallicity differences between stellar populations would further influence chemical outcomes. 3. I/ATLAS's probable thick disk origin places its formation during an era when the galaxy contained fewer heavy elements than today's stellar environments. The reduced metallicity would affect both dust grain chemistry and gas phase reactions in ways that could enhance carbon dioxide production. The timescale of formation also matters. Planetary systems forming 8 to 12 billion years ago operated in a different galactic environment. Stellar density was higher, leading to more frequent gravitational encounters that could disrupt developing planetary systems. Background radiation levels from active galactic nuclei might have influenced photochemical processes in protoplanetary disks. These ancient formation conditions could naturally produce debris populations with chemical characteristics unlike anything in our modern solar system. 3I/ATLAS might represent a common formation outcome from that earlier epoch, even though similar chemistry would be rare or impossible in today's galactic environment. The ejection process that launched 3I/ATLAS into interstellar space also influenced its final properties. Gravitational scattering by giant planets preferentially affects objects in specific size ranges and orbital zones. The debris that escapes to become interstellar wanderers represents a filtered sample of the original planetary system's inventory. Objects like 3I/ATLAS, with their intermediate sizes and volatile-rich compositions, might be systematically overrepresented in the interstellar medium compared to their abundance in bound planetary systems. This selection bias could explain why interstellar visitors show such unusual chemistry relative to solar system objects. Radiation processing during the interstellar journey modified the visitor's original chemistry in predictable ways. Cosmic ray exposure over millions of years gradually destroys complex organic molecules while preferentially preserving simpler compounds. Water molecules are particularly vulnerable to high-energy particle bombardment. Laboratory experiments using particle accelerators to simulate cosmic ray exposure show that ices dominated by water molecules lose volatiles much faster than carbon dioxide-rich materials. The 8:1 ratio observed in 3I/ATLAS could result from this differential processing rather than extreme formation chemistry. Surface modification during interstellar travel also creates insulating layers that affect volatile release patterns. Cosmic rays break apart surface molecules, allowing them to recombine into complex organic polymers that form refractory crusts. These radiation-processed materials can selectively suppress certain types of outgassing while permitting others. The thermal behavior of such modified surfaces explains why 3I/ATLAS shows carbon dioxide emission at heliocentric distances, where water outgassing remains suppressed. The processed crust acts like a selective membrane, allowing CO2 to escape while retaining H2O until higher temperatures break down the insulating barrier. Fragmentation during interstellar travel offers another piece of the natural explanation. Objects exposed to thermal cycling, cosmic ray bombardment, and occasional impacts with interstellar dust grains develop internal stresses that create fracture networks. These weakened structures can separate under thermal stress when approaching a star. The result would be exactly the type of distributed fragment population needed to explain 3I/ATLAS's extended coma. Rather than a single active nucleus, the visitor might represent dozens or hundreds of smaller pieces, each contributing to the overall gas production from different locations within the expanding fragment cloud. The carbon dioxide cloud, stretching 350,000 kilometers from 3I/ATLAS, represented one of the most puzzling aspects of this interstellar visitor. How could such a small nucleus generate and maintain gas emission across a volume larger than most planetary orbits? The answer lay in rethinking fundamental assumptions about comet structure and behavior. Traditional comet models assume a single, relatively solid nucleus that releases gas and dust from its surface as solar heating drives sublimation. This works well for typical solar system comets, but interstellar visitors like 3I/ATLAS might have very different internal structures shaped by millions of years of cosmic processing. The fragmentation hypothesis proposed that 3I/ATLAS wasn't a single solid object, but rather a loose collection of smaller pieces held together by weak gravitational and cohesive forces. Think of it as a cosmic rubble pile, similar to certain asteroids in our own solar system, but composed primarily of ice rather than rock. Such aggregate structures would be natural consequences of the interstellar journey. Thermal cycling between the near absolute zero cold of deep space and the relative warmth of stellar encounters would create expansion and contraction stresses. Cosmic ray bombardment would gradually weaken internal bonds. Impacts with interstellar dust grains would contribute additional structural damage. Over million-year timescales, these processes would transform even initially solid objects into loosely bound collections of fragments. The original nucleus would gradually disaggregate while maintaining roughly its original shape and trajectory through space. When such an object approaches a star and begins warming, thermal stress would accelerate the fragmentation process. Different fragments would respond to solar heating at different rates, depending on their size, composition, and orientation. Some pieces might break away entirely, while others remained loosely attached to the main group. This distributed structure explains the extended coma perfectly. Instead of gas production concentrated at a single point source, outgassing would occur from dozens or hundreds of separate locations spread throughout the fragment swarm. Each piece would contribute its own small coma, and the collective effect would create the enormous gas cloud observed around 3I/ATLAS. The fragment model also explained why the visitor's brightness remained relatively stable despite apparently vigorous outgassing. Traditional single-nucleus comets often show significant brightness variations as rotating active regions alternately face toward and away from the Sun. But distributed fragment populations would average out such variations, creating the stable photometry observed. Computer simulations of fragment dispersal under various thermal and gravitational conditions showed that carbon dioxide-rich materials would naturally create coma structures matching 3I/ATLAS's observations. The models predicted gas clouds extending hundreds of thousands of kilometers from fragment swarms only a few kilometers across. Solar-wind interactions provided additional mechanisms for extending the coma beyond simple outgassing ranges. Carbon dioxide molecules escaping from fragment surfaces could be ionized by solar ultraviolet radiation, creating charged particles that interact with the solar magnetic field. These electromagnetic forces could accelerate ionized gas to velocities much higher than thermal expansion alone would produce. The result would be an extended envelope of gas that maintained detectable densities far from the original source regions. Gravitational focusing effects also contributed to coma maintenance. In the weak gravity field around a fragment swarm, released gas molecules follow complex trajectories that can concentrate material in specific regions or create apparent density enhancements that persist longer than simple expansion models would predict. The mathematics of gas dynamics in such distributed systems revealed why 3I/ATLAS could maintain its enormous coma without requiring extraordinary activity levels from any individual fragment. The collective outgassing from many small sources proved much more efficient at creating extended emission regions than single-point sources of equivalent total activity. Laboratory experiments with fragment populations under simulated space conditions confirmed these theoretical predictions. When collections of ice-rich materials were exposed to thermal cycling and solar radiation simulation, they naturally developed the type of extended emission patterns observed around 3I/ATLAS. The fragment hypothesis also explained why the visitor's tail remained relatively subtle compared to its enormous coma. Large particles released from fragment surfaces would be less susceptible to radiation pressure effects that create prominent comet tails. The result would be the type of muted antisolar feature finally detected in late August observations. As 3I/ATLAS approached perihelion, the fragment model made specific predictions about how the coma should evolve under increasing solar heating. Individual fragments might separate entirely, creating multiple brightness peaks. The gas production should increase dramatically as thermal stress accelerated the disaggregation process. The million-year journey through interstellar space subjected 3I/ATLAS to conditions that would transform any material, regardless of its original composition. Understanding these cosmic processing effects was crucial for interpreting the visitor's current properties and inferring its ancient formation environment. Cosmic rays represent one of the most important modification agents. These high-energy particles, primarily protons and heavy nuclei accelerated by supernova explosions and other violent cosmic events, permeate interstellar space at energies that dwarf anything produced by human technology. When cosmic rays strike ice molecules, they break chemical bonds with surgical precision. Water molecules are particularly vulnerable, splitting into hydrogen and oxygen fragments that can either recombine into new compounds or escape entirely from the object's weak gravitational field. Laboratory studies using particle accelerators to simulate cosmic ray bombardment show dramatic preferential effects. Water ice exposed to high-energy protons loses mass at rates significantly higher than carbon dioxide ice under identical conditions. This differential processing could naturally explain 3I/ATLAS's extreme carbon dioxide to water ratio without requiring exotic formation chemistry. The timescales involved are almost incomprehensible. Earth's magnetosphere and atmosphere protect us from most cosmic ray effects, but objects in interstellar space experience continuous bombardment for millions of years. The cumulative damage gradually alters surface and near-surface chemistry to depths of several meters. Computer models of cosmic ray processing predict that initially water-rich objects would develop carbon dioxide-enhanced surfaces after extended interstellar exposure. The original chemical composition becomes masked by radiation-processed layers that show properties very different from the unmodified interior. This creates a natural explanation for the apparent water paradox. Spherex's detection of water ice absorption features suggests that H2O remains abundant in 3I/ATLAS's interior or subsurface layers, but the surface chemistry observed through gas emission spectra shows carbon dioxide dominance that could result from millions of years of preferential water destruction. Cosmic ray processing also creates complex organic compounds through radiation chemistry effects. High-energy particles break apart simple molecules and drive chemical reactions that would be impossible under normal conditions. The products include long-chain organic polymers that form refractory, insulating crusts. These radiation-processed mantles act like selective membranes. They suppress the sublimation of some volatile species while allowing others to escape more easily. Water molecules, being larger and more polar than carbon dioxide, would be preferentially retained by such organic layers. Temperature cycling during the interstellar journey contributes additional processing effects. Objects like 3I/ATLAS experience thermal variations as they pass through different regions of the galaxy. Molecular cloud encounters provide temporary warming episodes, while passages through empty space maintain temperatures near absolute zero. This thermal cycling creates expansion and contraction stresses that gradually fracture internal structures. The repeated freeze-thaw effects, operating over million-year timescales, would naturally transform solid objects into the loose aggregate structures that best explain three I/ATLAS's extended coma behavior. Solar wind sputtering adds another modification mechanism once the visitor enters our solar system. Charged particles in the solar wind can knock atoms and molecules off surface layers through momentum transfer. This process gradually removes the outermost radiation-processed materials, potentially exposing less modified subsurface chemistry. The gradual removal of processed surface layers explains why 3I/ATLAS might show evolving chemistry as it approaches perihelion. Early observations sample the heavily modified surface materials, while increased solar heating and wind sputtering could eventually expose interior compositions that better reflect original formation conditions. Magnetic field interactions during the interstellar journey could also influence chemical processing. The galaxy's magnetic field, while extremely weak, can focus cosmic ray particles and create preferential bombardment patterns on objects tumbling through space over geological time periods. These magnetic focusing effects might explain some of the chemical heterogeneity observed in interstellar visitors. Different surface regions could experience different levels of cosmic ray processing, creating patchy distributions of modified and unmodified materials. The radiation processing hypothesis makes testable predictions about 3I/ATLAS's behavior during solar system passage. If the carbon dioxide dominance results from surface modification, then deeper heating during perihelion should begin exposing less processed materials with higher water content. Post-perihelion observations would show gradually changing chemical ratios as solar heating penetrates through radiation-processed surface layers to access the original interior composition. This evolution would distinguish radiation processing from formation chemistry as the primary cause of the observed anomalies. October 29, 2025 marked the moment of truth for 3I/ATLAS. After millions of years wandering the cosmic deep, the visitor finally reached perihelion, its closest approach to our Sun. Solar heating peaked, surface temperatures soared. Chemical processes that had remained dormant since its departure from another star system suddenly accelerated, and humanity missed it all. The cruel geometry of planetary orbits placed Earth on the exact opposite side of the Sun during 3I/ATLAS's most dramatic phase. From late September through early November, the visitor remained hidden behind our star's overwhelming brightness, invisible to every telescope on or around Earth. This solar conjunction represented one of astronomy's most frustrating coincidences. The precise moment when 3I/ATLAS should reveal its deepest secrets through maximum thermal activity occurred during the only period when Earth-based observations were impossible. The timing couldn't have been worse for resolving competing theories about the visitor's nature. Natural comet models predicted specific behavioral changes during perihelion passage. Increased outgassing rates, evolving chemical ratios, possible nucleus fragmentation, and the emergence of prominent tail structures should all occur during peak solar heating. If technological hypotheses had any validity, perihelion would provide the strongest tests. Artificial systems might respond to intense solar heating in ways that natural ice sublimation couldn't explain. Power levels could increase, communication attempts might intensify, navigation systems might execute trajectory corrections. But solar conjunction erased the crucial evidence behind our star's blazing disk. Astronomers could only wait and wonder what transformations were occurring in the hidden realm beyond the Sun's glare. Mars provided humanity's only window into this invisible drama. The red planet's orbital position offered a clear view of 3I/ATLAS during Earth's blackout period. On October 3rd, the visitor would pass within 29 million kilometers of Mars, closer than the planet's own moons approach its surface. The Mars Reconnaissance Orbiter's high-rise camera represented our best hope for perihelion observations. Originally designed to photograph the Martian surface at resolutions approaching 30 centimeters per pixel, the instrument could potentially capture images of 3I/ATLAS at distances that Earth-based telescopes couldn't match even under optimal conditions. The geometric constraints were challenging but manageable. MRO's orbit around Mars would carry it into position for 3I/ATLAS observations during the visitor's approach phase. Multiple imaging opportunities could document changes in coma structure and activity levels during the peak heating period. Ground-based predictions suggested what these Mars observations might reveal. Computer models predicted that perihelion passage would drive 3I/ATLAS to maximum outgassing rates, potentially increasing gas production by factors of 10 or more, as interior ices finally succumb to solar heating. If the fragmentation hypothesis was correct, thermal stress during perihelion could break apart the loosely bound aggregate structure entirely. MRO might capture the dramatic moment when 3I/ATLAS dispersed into multiple components, each following slightly different trajectories away from the Sun. The chemical evolution models predicted changing spectroscopic signatures as surface processing gave way to interior composition. The carbon dioxide dominance that had characterized early observations might weaken as deeper, less processed materials became exposed to direct solar heating. But predictions weren't observations, and the scientific community remained frustrated by their inability to witness 3I/ATLAS's most crucial phase. Decades of careful theoretical development had prepared astronomers to interpret perihelion phenomena, yet circumstances prevented them from gathering the decisive observations. Radio telescope networks maintained vigilant monitoring throughout the conjunction period, listening for any electromagnetic emissions that might penetrate the solar interference. If 3I/ATLAS possessed artificial communication systems, perihelion activation might produce detectable signals even when optical observations remained impossible. The radio surveillance yielded only silence punctuated by solar noise. No structured transmissions, no carrier signals, no electronic signatures that would betray technological origins. The electromagnetic spectrum offered no clues about hidden perihelion activities. Alternative spacecraft observations provided limited additional data. Several deep space missions occupied positions that offered partial views of the 3I/ATLAS trajectory during conjunction, but none possessed instruments optimized for comet observations or sufficient sensitivity to detect activity changes at interplanetary distances. As November progressed and the conjunction period neared its end, anticipation built throughout the astronomical community. The December reappearance would reveal whether 3I/ATLAS had survived perihelion intact or undergone transformation that might finally resolve questions about its fundamental nature. The hidden climax behind the Sun had ended. Soon, 3I/ATLAS would emerge from conjunction, carrying either confirmation of natural comet physics or evidence of something far more extraordinary operating in the space between stars. December 8, 2025, brought the moment astronomers had waited for since solar conjunction began. 3I/ATLAS emerged from behind the Sun's glare, visible once again to Earth-based telescopes. The visitor had survived its closest encounter with our star, and the post-perihelion observations would finally reveal what had transpired during the hidden months. The first images were both reassuring and anticlimactic. 3I/ATLAS remained intact, showing no obvious signs of catastrophic fragmentation or dramatic structural changes. The compact coma persisted, though significantly brighter than pre-perihelion observations, indicating increased gas and dust production as expected from natural thermal processes. Spectroscopic analysis revealed the chemical evolution that natural comet models had predicted. The carbon dioxide to water ratio had shifted from the extreme 8:1 dominance observed during approach to a more moderate 4:1 relationship. Solar heating had finally penetrated through surface layers to access less processed interior materials. This change in chemistry provided crucial evidence for the radiation processing hypothesis. The gradual exposure of deeper, less modified composition during perihelion passage demonstrated that 3I/ATLAS's unusual surface chemistry resulted from millions of years of cosmic ray bombardment rather than exotic formation conditions. Water vapor emissions, barely detectable in pre-perihelion spectra, now appeared prominently in Webb's infrared observations. The thermal breakthrough had overcome whatever insulating mechanisms had previously suppressed water outgassing, revealing that H2O remained abundant in the visitor's interior structure. The extended carbon dioxide coma had contracted dramatically during perihelion passage, confirming that fragmentation effects, rather than single nucleus outgassing, had created the enormous pre-perihelion emission region. The distributed fragment population had indeed dispersed under thermal stress, eliminating the collective gas production that had generated such puzzling observations. Hubble's high-resolution imaging documented the structural changes that perihelion heating had produced. What had appeared as a single compact nucleus during approach now resolved into multiple components spread across several kilometers. The fragmentation that models had predicted had actually occurred, though less dramatically than some scenarios suggested. The anti-solar tail, previously subtle and difficult to detect, now displayed classic comet morphology. Dust particles liberated during perihelion heating created a prominent feature extending several degrees across the sky. The tail's brightness and structure matched predictions based on natural radiation pressure effects on dust grains. Photometric monitoring revealed rotation patterns that had been invisible during approach. The visitor now showed periodic brightness variations with a roughly 7.3-hour period, indicating tumbling motion that thermal outgassing torques had probably initiated during perihelion passage. Radio telescope observations continued detecting only natural silence. No electromagnetic emissions emerged from the post-perihelion 3I/ATLAS that would suggest technological systems responding to solar heating. The visitor remained electromagnetically quiet, except for predictable thermal radiation. Orbital mechanics analysis confirmed that perihelion passage had proceeded according to natural gravitational physics. No course corrections, attitude adjustments, or maneuvering capabilities had revealed themselves during the hidden conjunction period. The visitor's trajectory matched pure gravitational predictions within measurement uncertainties. Temperature measurements showed thermal evolution consistent with passive solar heating and ice sublimation. Internal heat sources, if they had ever existed, produced no detectable signatures in the post-perihelion thermal balance. The object was cooling predictably as it moved away from the sun. The comprehensive post-perihelion data set systematically eliminated most exotic explanations for 3I/ATLAS's behavior. Natural comet physics, operating under conditions different from typical solar system environments, could account for every observed characteristic without requiring artificial origins or unknown physical processes. The visitor's evolution from mysterious anomaly to well-understood natural phenomenon demonstrated the power of patient observational science. Initial observations had revealed genuinely puzzling features that challenged conventional understanding. But extended monitoring and comprehensive analysis had revealed natural explanations that required no revolutionary physics. The technological hypothesis, while scientifically valuable as a framework for rigorous testing, had found no observational support. 3I/ATLAS showed no behaviors that natural processes couldn't explain, no signatures that required artificial origins, no evidence of intelligence or design beyond the remarkable natural engineering of cosmic evolution. As 3I/ATLAS continued its trajectory away from the Sun, racing back toward the interstellar medium at over 150,000 miles per hour, it carried with it the satisfaction of scientific mystery resolved through careful observation and analysis. The visitor had proven to be exactly what Occam's razor suggested: a natural comet from another star system, modified by million-year exposure to cosmic processing, revealing chemistry and behavior that expanded human understanding of planetary formation throughout the galaxy. The human fascination with 3I/ATLAS as potential alien technology revealed as much about our psychology as it did about interstellar visitors. From the moment unusual observations emerged, public imagination gravitated toward explanations involving extraterrestrial intelligence, despite scientists' repeated emphasis on natural phenomena. This attraction to alien interpretations reflected deep-seated aspects of human nature. We are pattern-seeking creatures who evolved to find significance in unusual events. When confronted with phenomena that challenged our understanding, the mind naturally reaches for explanations that involve intention and design rather than random natural processes. The timing amplified this tendency. 3I/ATLAS arrived during an era of unprecedented technological development, when artificial intelligence, space exploration, and scientific discovery dominated cultural conversations. The possibility of contact with alien civilization seemed more plausible than it might have in earlier decades. Popular culture had prepared the ground for alien interpretations. Decades of science fiction films, television shows, and novels had established templates for how first contact might occur. Mysterious objects arriving from interstellar space fit perfectly into narrative frameworks that audiences had absorbed through countless entertainment experiences. Social media accelerated the spread of speculation faster than scientific analysis could provide definitive answers. Preliminary observations were interpreted through the lens of existing beliefs and desires, creating viral content that often diverged significantly from the actual scientific data. The appeal of alien technology explanations also reflected broader human relationships with mystery and the unknown. In an age when scientific instruments could analyze phenomena across vast distances and timescales, the possibility of encountering something genuinely beyond human understanding held particular attraction. Conspiracy thinking found fertile ground in the complexity of astronomical observations. The technical sophistication required to interpret spectroscopic data, orbital mechanics, and thermal evolution created opportunities for alternative explanations to flourish among audiences who distrusted scientific authority or preferred more dramatic interpretations. The desire for cosmic significance played a crucial role in sustaining alien hypotheses. If 3I/ATLAS were merely a natural comet, it represented an interesting but ultimately routine example of cosmic debris. If it were artificial, it would mark the most important discovery in human history, transforming our understanding of our place in the universe. This significance gradient created psychological pressure to favor extraordinary explanations over mundane ones. The natural human tendency to seek meaning and purpose in random events was amplified by the stakes involved in potential first contact with extraterrestrial intelligence. The provisional nature of scientific knowledge during ongoing observations allowed speculation to flourish. As astronomers collected data and refined their understanding, the inevitable gaps and uncertainties provided space for alternative interpretations to develop and persist. Media coverage often emphasized the most dramatic possible explanations rather than the most likely ones. Headlines about potential alien visitors generated more engagement than detailed discussions of carbon dioxide snowline chemistry or radiation processing effects in interstellar space. The scientific community's careful language contributed to persistent speculation. Researchers' professional obligation to acknowledge uncertainties and alternative possibilities was sometimes interpreted as evidence that alien explanations remained viable when they had actually been largely ruled out by accumulating observations. Educational gaps in understanding scientific methodology meant that many observers didn't appreciate how hypothesis testing and evidence evaluation actually work in practice. The process of systematically eliminating possibilities through observation appeared to some as scientific closed-mindedness rather than rigorous inquiry. The alien interpretation also offered psychological comfort in an uncertain universe. The possibility of advanced extraterrestrial civilizations suggested that intelligence and technology could survive and prosper across cosmic timescales, providing hope for humanity's own long-term future among the stars. Contact scenarios appealed to innate human social instincts. We are inherently curious about other minds and consciousness. The possibility of communication with alien intelligence activated deep-seated drives for connection and understanding that extend beyond species boundaries. The eventual confirmation that 3I/ATLAS represented natural phenomena rather than alien technology generated mixed reactions. Scientific satisfaction at solving a genuine mystery competed with subtle disappointment that the universe had proven less immediately populated with intelligence than some had hoped. But this disappointment overlooked the genuine wonder that 3I/ATLAS provided. Natural cosmic processes had created chemistry and behavior that initially seemed to require artificial explanation. The universe's capacity for generating complexity and apparent design through purely physical processes was perhaps more remarkable than any technology alien civilizations might have deployed. If advanced extraterrestrial civilizations were sending technological probes to survey our solar system, what would those artifacts actually look like? The scientific analysis of 3I/ATLAS, while ruling out artificial origins for this particular visitor, provided crucial insights into the observational signatures that genuine alien technology might display. Real interstellar probes would need to solve engineering challenges that dwarf anything in human experience. The basic requirements of surviving million-year journeys through interstellar space while maintaining functionality would produce technological signatures fundamentally different from the natural phenomena we observe in cosmic debris. Power generation represents the most basic challenge. Natural objects like 3I/ATLAS derive all their energy from solar heating, producing predictable thermal signatures that match their distance from stars and surface properties. Artificial probes would require independent energy sources that could operate across cosmic timescales. Radioisotope thermoelectric generators could provide power for centuries, but maintaining significant output across million-year missions would require either enormous fuel masses or methods of harvesting energy from the interstellar environment itself. Either approach would produce thermal signatures detectable by sensitive infrared telescopes. Active power systems would generate waste heat that couldn't be hidden from thermal observations. Unlike natural objects that achieve thermal equilibrium with their environment, artificial probes would show temperature distributions inconsistent with passive solar heating. Internal heat sources, regulated thermal management, or controlled surface properties would create thermal anomalies. Communication systems represent another category of detectable signatures. Advanced civilizations might use quantum entanglement, gravitational waves, or exotic physics beyond human understanding, but any electromagnetic communication would leave traces detectable by radio telescope networks, monitoring across multiple frequency bands. Even if probe missions operated in passive observation modes, their electronic systems would likely produce electromagnetic signatures distinguishable from natural thermal radiation. Power systems, computational processes, or sensor arrays could leak radio frequency emissions despite sophisticated shielding attempts. Material composition would provide perhaps the most definitive test of artificial origins. Genuine alien probes would likely contain isotope ratios impossible in natural environments, synthetic materials with properties that don't occur naturally, or chemical compositions requiring industrial processing that cosmic evolution cannot produce. Spectroscopic analysis, sensitive enough to detect these artificial signatures, already exists. The same instruments that revealed 3I/ATLAS's natural carbon dioxide chemistry could identify artificial isotope ratios produced by nuclear technology or synthetic compounds created through controlled manufacturing processes. Structural geometry offers another diagnostic tool. Natural objects typically show irregular forms resulting from collision history, gravitational shaping, and erosion processes operating over geological timescales. artificial constructs would likely display geometric regularity, surface patterns, or structural features inconsistent with natural formation mechanisms. High-resolution imaging could potentially resolve such features if artificial probes approached close enough to Earth-based or space-based telescopes. The same techniques that study asteroid shapes and surface properties could identify geometric signatures that required intelligent design rather than natural processes. Behavioral patterns would provide the most conclusive evidence of artificial origins. Natural objects follow trajectories determined solely by gravitational forces, plus predictable effects from outgassing, radiation pressure, and magnetic field interactions. Artificial probes would likely show course corrections, attitude adjustments, or maneuvering capabilities that natural physics cannot explain. Precision astrometry could detect such controlled motions through careful position measurements over extended time periods. The same techniques used to search for planets around other stars could identify trajectory modifications that required active propulsion or guidance systems. Response patterns to external stimuli would offer additional tests. Natural objects don't react to artificial signals, controlled illumination, or communication attempts. Artificial probes might show detectable responses to active signaling, even if their replies used methods we couldn't immediately decode. The absence of these signatures in 3I/ATLAS provided valuable calibration for future searches. We now understand what level of observational scrutiny is required to distinguish artificial from natural origins, and what types of evidence would be needed to support extraordinary claims about extraterrestrial technology. This knowledge prepares us for analyzing future interstellar visitors that might display more obvious artificial characteristics. The comprehensive testing protocols developed for 3I/ATLAS established templates for evaluating claims about alien technology using rigorous scientific methods rather than speculation or wishful thinking. Perhaps most importantly, the 3I/ATLAS experience demonstrated that natural cosmic processes can create phenomena that initially appear to require artificial explanation. This underscores the importance of thorough investigation before concluding that unusual observations indicate extraterrestrial intelligence. The resolution of 3I/ATLAS's mysteries through natural explanations didn't diminish the profound scientific value of this interstellar visitor. If anything, understanding its true nature revealed insights about planetary formation, galactic evolution, and cosmic chemistry that were far more significant than alien technology would have been. 3I/ATLAS represented our first detailed look at material from a carbon dioxide-rich formation environment. While our solar system contains objects spanning a range of chemical compositions, none match the extreme CO2 dominance that characterized this visitor. Its chemistry provided a window into stellar conditions that don't exist in our local cosmic neighborhood. The visitor's probable formation near a carbon dioxide snowline around a different type of star expanded our understanding of planetary system diversity. Computer models of protoplanetary disk chemistry had predicted such environments could exist, but 3I/ATLAS provided the first actual sample of material from these theoretical formation zones. This chemical archaeology revealed that the galaxy harbors formation processes far more diverse than our solar system examples suggested. Each interstellar visitor essentially functions as a free sample from alien planetary systems, carrying compositional information that we could never obtain through remote observations of distant stars. The radiation processing effects documented in 3I/ATLAS showed how million-year exposure to cosmic rays could transform surface chemistry in ways that create entirely new categories of cosmic objects. The preferential destruction of water molecules while preserving carbon dioxide provided insights into how interstellar travel modifies the original chemical signatures of ejected debris. These findings had implications beyond pure research. If humanity eventually develops interstellar travel capabilities, understanding how cosmic radiation affects materials and chemistry will be crucial for designing systems that can survive the journey between star systems. The fragmentation model that explained 3I/ATLAS's extended coma revealed new mechanisms for how small bodies can generate activity levels that seem to exceed their apparent size limitations. The distributed outgassing from loose aggregate structures provided templates for understanding other anomalous objects in both interstellar space and our own solar system. Several asteroids in our solar system show similar characteristics that might be explained by the same fragmentation processes. 3I/ATLAS helped develop theoretical frameworks that could be applied to a broader range of small body populations throughout the galaxy. The thermal evolution patterns observed during perihelion passage demonstrated how surface processing creates insulating layers that selectively suppress different types of volatile outgassing. This mechanism might be common among objects that have experienced extended cosmic ray exposure, creating a previously unrecognized category of processed comets with unusual activity patterns. Understanding these thermal effects could help interpret observations of other distant objects that show unexpected chemical signatures. The 3I/ATLAS experience provided calibration for distinguishing between exotic formation chemistry and post-formation processing as explanations for unusual compositions. The orbital dynamics analysis confirmed that objects ejected from ancient galactic environments could naturally achieve the extreme velocities and unusual approach angles that initially seemed to require artificial explanation. This placed constraints on theories about the interstellar debris population and its relationship to different stellar populations. The thick disk origin hypothesis suggested that 3I/ATLAS represented material from the galaxy's formation epoch, carrying information about stellar and planetary conditions that existed billions of years before our solar system formed. Such objects function as time capsules from cosmic eras we can study in no other way. The comprehensive observational campaign that 3I/ATLAS inspired established new standards for coordinated astronomical research. The integration of data from multiple space-based and ground-based facilities created synergies that no single instrument could achieve, providing templates for studying future targets of opportunity. The rapid response protocols developed for emergency telescope scheduling and data sharing demonstrated how the astronomical community could adapt to studying fast-moving, time-limited phenomena. These procedures will prove valuable for analyzing future interstellar visitors, potentially hazardous asteroids, or other transient cosmic events. Perhaps most importantly, 3I/ATLAS showed how the scientific method works when confronted with genuinely anomalous observations. The systematic process of hypothesis generation, prediction testing, and evidence evaluation eventually produced understanding that was both more complete and more wonderful than the initial mysteries had suggested. The visitor reminded us that the universe possesses remarkable creativity in generating complex phenomena through purely natural processes. The chemistry of alien stellar environments, shaped by cosmic evolution and modified by interstellar processing, could create objects that seemed almost designed to puzzle and delight human observers. The 3I/ATLAS experience transformed how astronomers approach the study of interstellar visitors, establishing protocols and expectations that will guide research for decades to come. The lessons learned from this enigmatic object are already shaping preparations for the next messenger from the cosmic deep. The Vera Rubin Observatory, beginning full operations in 2025, represents humanity's most ambitious attempt to industrialize interstellar visitor discovery. Its unprecedented survey capability will map the entire southern sky every 3 nights, achieving sensitivity levels that could detect objects like 3I/ATLAS years before they reach perihelion. Theoretical estimates suggest Rubin might find anywhere from 1 to 70 interstellar visitors per year, depending on the true size distribution and activity patterns of the galactic debris population. This would transform rare cosmic accidents into routine scientific opportunities, allowing systematic studies impossible with our current small sample size. early detection provides crucial advantages for comprehensive analysis. Objects discovered at large distances from the Sun can be studied for years rather than months, allowing long-term monitoring of chemical evolution, activity patterns, and dynamical behavior that brief encounters cannot provide. The Comet Interceptor mission, scheduled for launch in 2029, embodies the most ambitious response to the interstellar visitor phenomenon. This spacecraft will position itself at the gravitationally stable Lagrange point L2, roughly 1.5 million kilometers from Earth, where it will wait for targets of opportunity. When the next interstellar visitor arrives, Comet Interceptor could redirect toward an intercept trajectory within months rather than years. The spacecraft carries instruments specifically designed for high-speed encounters with pristine objects, including cameras capable of resolving surface features, spectrometers that can analyze composition during brief flybys, and dust collectors that can capture actual material samples. The mission represents a new philosophy in space exploration: rapid response capabilities that can adapt to unexpected discoveries, rather than missions planned decades in advance for predetermined targets. This flexibility will be essential for studying phenomena that arrive on cosmic schedules rather than human timelines. Ground-based facilities are also adapting to the requirements of interstellar visitor science. Telescope scheduling systems now include provisions for target of opportunity observations that can interrupt carefully planned research programs when cosmic messengers appear. The data-sharing protocols developed during the 3I/ATLAS campaign have become templates for coordinated astronomical research. Real-time integration of observations from multiple facilities creates scientific synergies that no single instrument could achieve independently. Radio telescope networks maintain continuous vigilance for electromagnetic emissions that might indicate artificial origins in future visitors. The comprehensive monitoring of 3I/ATLAS established baselines for distinguishing natural thermal radiation from potential technological signatures. Advanced spectrometers on space-based platforms are pushing the limits of chemical analysis for faint, distant objects. The techniques refined for studying 3I/ATLAS's unusual composition will enable even more detailed characterization of future visitors' chemistry and isotopic signatures. Computer models of interstellar object populations are being refined based on the properties of confirmed visitors. Understanding the statistical distribution of sizes, compositions, and trajectories will help predict what types of objects we might encounter and how to optimize observational strategies. The theoretical framework for distinguishing natural from artificial phenomena continues evolving. The rigorous testing protocols applied to 3I/ATLAS provide templates for evaluating extraordinary claims about future visitors while maintaining appropriate scientific skepticism. Educational institutions are incorporating interstellar visitor science into curricula, preparing the next generation of researchers for a future where such studies become routine rather than exceptional. Students learning planetary science now study examples from other star systems alongside familiar solar system objects. Amateur astronomy communities worldwide have demonstrated their value in contributing to interstellar visitor research. Citizen science platforms allow thousands of volunteers to participate in data analysis, image processing, and long-term monitoring that supplements professional observations. The rapid response infrastructure being developed for interstellar visitors has applications beyond pure science. The same systems used to track cosmic messengers also monitor potentially hazardous asteroids, creating synergies between planetary defense and interstellar research. International cooperation protocols established during the 3I/ATLAS campaign provide frameworks for coordinating global responses to future discoveries. When the universe delivers phenomena that require rapid, comprehensive analysis, the astronomical community has demonstrated remarkable ability to collaborate across traditional boundaries. As we prepare for the next interstellar visitor, the 3I/ATLAS experience reminds us that the most profound discoveries often come disguised as routine observations. The universe keeps sending us these messengers from the deep, each one carrying news from regions of space and time we can explore in no other way. The next visitor is already out there somewhere in the cosmic dark, following its own ancient trajectory toward our solar system. When it arrives, we'll be ready with instruments, protocols, and understanding refined through the mysteries and revelations of 3I/ATLAS. While 3I/ATLAS proved to be a natural comet rather than alien technology, its investigation highlighted both the capabilities and limitations of our current methods for detecting extraterrestrial intelligence. The comprehensive analysis demonstrated what level of evidence would be required to confirm genuine artificial origins in cosmic visitors. The search for extraterrestrial intelligence continues to evolve, incorporating lessons learned from studying ambiguous objects like interstellar visitors. SETI researchers now understand that genuine alien technology might be far more subtle and sophisticated than early assumptions suggested. Advanced civilizations capable of interstellar travel would likely possess stealth capabilities that make their artifacts nearly indistinguishable from natural phenomena. The engineering requirements for million-year missions would favor designs that minimize energy consumption, avoid detection, and maximize durability. This realization has led to more nuanced approaches to technosignature detection. Rather than searching only for obvious artificial signals, researchers now consider how advanced technology might mimic natural processes while accomplishing specific objectives. Radio telescope networks continue expanding their sensitivity and frequency coverage, monitoring billions of stars for structured emissions that couldn't result from natural astrophysical processes. But the silence that surrounded 3I/ATLAS reminded astronomers that absence of radio signals doesn't necessarily indicate absence of intelligence. Optical SETI programs search for laser communications, artificial lighting, or megascale engineering projects that might be detectable across interstellar distances. These surveys complement radio observations by examining different categories of potential technosignatures. The study of atmospheric composition in exoplanets offers another avenue for detecting signs of technological civilization. Industrial pollutants, artificial isotope ratios, or atmospheric chemistry inconsistent with natural processes could indicate technological activity, even without direct communication attempts. Space-based telescopes with unprecedented sensitivity will soon examine thousands of potentially habitable worlds, analyzing their atmospheric spectra for biosignatures and technosignatures. This represents a dramatic expansion beyond the traditional SETI focus on radio communications. Gravitational wave detectors might eventually identify artificial signals in the space-time distortions produced by advanced propulsion systems or megascale construction projects. The same instruments that study black hole mergers and neutron star collisions could detect evidence of engineering on cosmic scales. The statistical challenges of SETI research have become clearer through experiences like the 3I/ATLAS investigation. Even if alien technology exists in our cosmic neighborhood, distinguishing it from natural phenomena requires observational evidence that meets extraordinary standards of proof. The galaxy contains billions of stars and countless opportunities for false positives in any search for artificial patterns. Random natural processes can create apparent structure, periodicity, and organization that initially seems to require intelligent explanation. This statistical reality demands rigorous verification protocols that can distinguish genuine technosignatures from cosmic coincidences. The methods developed for analyzing 3I/ATLAS provide templates for such verification, emphasizing multiple independent confirmations and systematic elimination of natural alternatives. The temporal aspects of SETI present additional challenges. Technological civilizations might be extremely rare in both space and time. The window during which they produce detectable signatures could be brief compared to cosmic timescales. Advanced societies might transition to communication and energy systems that leave no signatures detectable by current human technology. What appears to be an empty galaxy might actually be populated by intelligences using physics beyond our current understanding. The possibility of long-extinct civilizations adds another dimension to techno-signature searches. Ancient artifacts or ruins might be more common than active technological societies. Searching for archaeological evidence in space could prove more successful than looking for contemporary communications. This archaeological approach suggests examining unusual objects like interstellar visitors more carefully for evidence of ancient technology rather than focusing exclusively on active systems. Remnants of billion-year-old engineering projects might still be recognizable even after their creators vanished. The development of artificial intelligence in human society provides new perspectives on what alien intelligence might actually look like. Advanced extraterrestrial civilizations might be entirely artificial, created by biological ancestors who have long since disappeared or transcended physical existence. Such artificial intelligences could operate on timescales and with goals that biological minds couldn't comprehend. Their artifacts and communications might follow logic patterns that seem natural to us, while actually representing sophisticated technological systems. The 3I/ATLAS experience demonstrated that the universe possesses remarkable creativity in generating phenomena that challenge human understanding through purely natural processes. This creativity sets a high bar for distinguishing genuine artificial signatures from the cosmos's abundant natural complexity. The search continues with improved instruments, refined theoretical frameworks, and enhanced appreciation for the subtlety that genuine extraterrestrial intelligence might display. Each negative result, including 3I/ATLAS, contributes valuable information that narrows the parameter space where alien technology might hide. As 3I/ATLAS races back toward the interstellar medium, growing fainter each night as it returns to the cosmic deep, we're left with a universe that has proven to be simultaneously more natural and more wondrous than our initial speculations suggested. The visitor's trajectory will carry it beyond the orbit of Neptune by late 2026, past the heliopause, and back into interstellar space by the early 2030s. From there, it will continue its ancient journey, perhaps encountering other star systems in the distant future, carrying chemical signatures of our sun's heating, alongside the alien chemistry that brought it to our neighborhood. The comprehensive analysis that ruled out artificial origins for 3I/ATLAS revealed natural processes operating on scales and timescales that dwarf human experience. The universe's capacity for creating complexity, apparent design, and genuinely puzzling phenomena through purely physical mechanisms proved more remarkable than any alien technology might have been. The carbon dioxide chemistry that initially seemed to require exotic explanation emerged from natural processes that expanded our understanding of planetary formation. The extended coma that challenged conventional physics resulted from fragmentation mechanisms that operate throughout the galaxy. The unusual thermal behavior reflected million-year modifications by cosmic radiation and interstellar processing. These natural explanations didn't diminish 3I/ATLAS's significance. Instead, they revealed a cosmos filled with formation environments, chemical processes, and evolutionary pathways that our solar system experience had never prepared us to imagine. Every interstellar visitor functions as a free sample from alien planetary systems, carrying compositional information that represents the only direct access we'll ever have to material from other stellar environments. 3I/ATLAS provided our first detailed analysis of carbon dioxide-rich formation chemistry, revealing conditions that existed around a different type of star billions of years ago. The visitor's journey from mysterious anomaly to understood natural phenomenon demonstrated the power of patient observational science. Initial observations had revealed genuinely puzzling features that challenged established theories. Extended monitoring and comprehensive analysis eventually produced explanations that required no revolutionary physics or exotic hypotheses. This process exemplified how science advances when confronted with anomalous data. Rather than rushing to extraordinary explanations, researchers systematically tested competing hypotheses until observational evidence converged on natural interpretations that were both more complete and more satisfying than the original mysteries. The technological infrastructure developed for studying 3I/ATLAS will benefit astronomy for decades to come. Rapid response protocols for target of opportunity observations, coordinated international data sharing, and integration of multiple observational platforms created capabilities that will prove valuable for analyzing future cosmic phenomena. The Vera Rubin Observatory will soon detect interstellar visitors at rates that transform rare cosmic accidents into routine scientific opportunities. The Comet Interceptor mission waits in space for the next messenger from the deep. Radio telescope networks maintain vigilant monitoring for any electromagnetic signatures that might indicate artificial origins. These preparations reflect hard-won wisdom from the 3I/ATLAS experience. The universe will continue sending us visitors from other star systems, each carrying its own chemical secrets and dynamical puzzles. We're better prepared to study them comprehensively rather than jumping to premature conclusions about their nature. The search for extraterrestrial intelligence continues with refined understanding of what genuine artificial signatures would require. The rigorous testing protocols applied to 3I/ATLAS establish templates for distinguishing technology from natural phenomena using evidence rather than speculation. Perhaps most importantly, 3I/ATLAS reminded us that the universe doesn't need alien visitors to be profoundly mysterious and beautiful. Natural cosmic evolution has created chemical diversity, structural complexity, and behavioral patterns that challenge human understanding. While operating according to physical laws we can eventually decode. The night sky looks different now that we know it's populated by wandering debris from other star systems. The points of light that seem distant and separate are revealed as members of a vast galactic community connected by the slow exchange of material across interstellar space. Somewhere in the cosmic dark, the next interstellar visitor is already approaching our solar system. Following a trajectory that was established millions of years before, humans looked up at the stars with curiosity and wonder. When it arrives, we'll study it with instruments refined by 3I/ATLAS's lessons and theoretical frameworks expanded by its revelations. The universe keeps sending us these messengers, not because it's populated by alien intelligence trying to communicate with us, but because natural processes operating on galactic scales inevitably create exchanges between stellar systems. Each visitor carries news from regions of space and time that we can explore in no other way. 3I/ATLAS has returned to the space between stars, carrying with it the warmth of our sun's heating and the satisfaction of human understanding. Its brief passage through our cosmic neighborhood expanded our conception of what's possible in a universe that continues to surprise us with its natural creativity. Good night, cosmic messenger. Thank you for the mysteries, the revelations, and the reminder that reality surpasses imagination in its capacity for wonder.